Okay, good afternoon, everyone, and welcome to the Charles David Keeling Lecture. I'm Jeff Trapp, head of the Department of Atmospheric Sciences here at the University of Illinois Urbana-Champaign. Thanks for joining us today. As a courtesy, we ask that you please keep your sound muted and your video off. For your reference, this talk will be recorded and made available at a later date on YouTube. Please check the IC website, which we'll put in the chat later, for more information. Now, before our speaker is introduced, I'd like to give you just a little background about the Keeling Lecture. This event is named for Charles David Keeling, a 1948 University of Illinois graduate from the Department of Chemistry, who determined how to make extremely precise measurements of atmospheric carbon dioxide. These measurements clearly indicated that the atmospheric CO2 concentrations were, and still are, increasing, leading to the recognition that human activities could have a significant impact on the Earth's climate system. After receiving his PhD in chemistry from Northwestern in 1954, Keeling spent most of his career at the Scripps Institution of Oceanography until his death in 2005. As the first to confirm the accumulation of atmospheric CO2, he produced a data set now known widely as the Keeling curve, and his measurements are renowned as the single most important environmental data set taken in the 20th century. Each year, a collaboration between academic units on campus results in a lecture on climate to honor Keeling's legacy. This year's lecture is co-sponsored by the Department of Atmospheric Sciences and the Institute for Sustainability, Energy, and Environment. And our lecturer is Dr. Gavin Schmidt. Here is Professor Christy Prostasescu to continue with the introduction. Christy?
Thank you. Hi, everybody. I'm Christy Prostasescu. I'm an assistant professor in atmospheric science and geology. And this afternoon, I have the honor to introduce to you one of the climate scientists I most admire, Dr. Gavin Schmidt. Dr. Schmidt holds a BA in mathematics from GISS College, Oxford, and a PhD in applied mathematics from the University College London. Since 2014, he is the director of the NASA Goddard Institute for Space Studies, or NASA GISS, where he's also the principal investigator for the GISS Model E Earth System model. Dr. Schmidt's research interests lie in understanding variability of the climate system, both internal variability and the response to external forcing, with a focus on how forced and unforced variations relate to each other. He's also done work in helping us understand how past climate variations can help constrain future climate change. In addition to his contributions to climate modeling and the physics of the climate system, Dr. Schmidt is also one of the world's preeminent climate communicators. He was one of the co-founders in 2004 of the Real Climate blog, sort of blogs are sort of a long form Twitter. At the time, this blog was critical in providing nuanced commentary on current topics in climate science to the broad public and to journalists. From February 2021 to January 2022, he was also the acting senior advisor on climate to the NASA administration, and his contributions were widely recognized. For example, in 2011, he was named Earth Sky Science Communicator of the Year, and the American Geophysical Union awarded him the inaugural Climate Communications Prize for work on communicating climate change issues to the public. It's a real pleasure to have you here, Gavin. And without further ado, take it away.
Okay, well, thank you very much, Christy. Thank you very much, everyone else, for inviting me, and thank you, participants, for taking an hour out of your time to be here. I normally, for a named lecture like this, one starts off with some key interaction that one had back in the day with the person who the lecturer is named after, but I have nothing. I never interacted with Dave Keeling, though I do know his son quite well. But I did watch a play based on his life a little bit, which I put the link in the chat. So that's as close as I get to Dave Keeling. Okay, so let me bring up my talk. Okay, great. So I'm going to talk about climate modeling, which is the the counterpart of all the observations that we're making. It's what we use to understand the observations and then to project those forward. So I'm going to try and answer a few questions here, and you may have other questions, so feel free to chime in if you think that I can answer them. Are we making any progress in climate modeling? Are we actually learning anything new? I'll try and answer that one. But is it even useful? I mean, even if the best models in the world, are we able to make use of them in a sensible way? And where do we go from here? What are the next steps in climate modeling? And I'll try and address all of those in various ways as we go through the talk. So have we made progress? Well, yes. I mean, so this is a climate model from the 1970s. It's one line of what was then the GISS climate model, written on a Fortran punch card. Some of you may remember these things. This was for the IBM 360 that we had in our on our second floor at GISS. Each one of those colored chunks is a subroutine. Everything has to be put in order. It would take you a day to put it in and a month to get an answer out. That was another world. These days, we have a lot better ways of visualizing the output that comes from these models. This is a simulation with the GMAO model. This is a reanalysis model. And what you're looking at here are particles in the atmosphere that have been highlighted. So the yellow is desert dust that's been lifted by the winds from the desert areas and kind of lofted, in this case, into the Atlantic. The blue is sea salt that's been carried up by the winds from the ocean by storms. You can see the white wispiness, particularly in northern China there. That's sulfate pollution from the burning of dirty coal. Each of those red dots is a fire that's burning, and they're producing carbonaceous aerosols. So that's kind of organic carbon, black carbon soot, and that's in the green. And you can see a lot of the different things that are happening in the climate system. And I want to point out a couple of salient features. One is that it's clear that all of the aerosols and the particles and the weather systems are all interacting in a very complex way. So the climate is inherently complex, and you can see that the constituents of the climate are being moved around by the weather, but in turn they are affecting the weather because they're radiatively active. They interfere with the sun's radiation and the radiation from the surface, and so they're changing the climate. How those aerosols changes the climate as well. And so everything there is just like an interaction. And then we have force things. So you can just see there's a volcano that just went off north of Madagascar. That's putting a lot of sulfur dioxide, and then that becomes sulfate particles into the atmosphere. And you can see that you've got both these natural internal variabilities, these external changes because of pollution, because of greenhouse gases, because of volcanoes, and it all kind of comes together in this big soup. But the key thing about climate modeling, though, which people often don't realize, is that there's no single line of code that says make a storm in the North Atlantic. There's no single line of code that says make an atmospheric river or a tropical cyclone or make the winds go this way or that way. Instead, all of these patterns that you're seeing are emergent properties from many, many different aspects of the code, right? The rotation of the Earth, convection, the large-scale circulation, noise, pollution, all of these things are interacting. And the patterns that we see are the sum total of all of those things. And so when I look at these patterns and you say, oh, well, I can see a storm here, I can see... those are emergent properties, and they're the ones that we really want to understand how they're changing, why they're changing as we change the overall climate system. And we are changing the climate system. understanding the climate is not just an academic exercise. It actually has very real and important implications, as I'm sure you are all aware. This is a graph of 4 different estimates of how the global surface temperatures are changing, how they have changed since the late 19th century. And you can see that, that there's a little bit of variation among those different products based on, the data that they're inputting, the methodology that they use, how they do the interpolation. But the basic picture is very, very clear. Since the 19th century, the planet has warmed by over 1 degree Celsius. That's about 2 degrees Fahrenheit. And people often ask me, well, why is that important? That doesn't seem like a very big number. And, if we were all in a room together here, if people remember what that was like, if we were all in the room here, then the temperature of the room would have gone up by about 2 degrees Fahrenheit just from us sitting around and radiating our own heat. But nobody would have gone extinct, and the chairs wouldn't have melted, and nothing terrible would have happened. So the question is always like, is this an important measurement? Is this an important difference that we've seen? And the answer is yes. Yes, it is, because the scale of temperatures that the planet experiences in the global mean is actually pretty restricted. If we go back to the last ice age, when both New York, where I am now, and Illinois, where you are now, was covered in ice, sea level was about 120 meters lower than it is now. The overall temperature change was only about 8 to 9 degrees Fahrenheit colder than the pre-industrial. And so this 2 degrees Fahrenheit change that we've just seen in the last 100 years, that's about 1/4 of an ice age unit, right? So it's gone up about 1/4 as much as the ice age was cold. And the projections that we have for the worst case scenarios kind of in 2100 are a full ice age unit. So as warm in the next 100 years as the ice age was cold. And that's a tremendous shift. And the ice age was a very, very different time, a very, very different planet, and we would expect no less by 2100. And so these are big and important numbers. But we can already tell that the planet is noticing these things. Right? We can go anywhere pretty much where we have old photographs of ice. Right? This is from the Mendenhall Glacier in Alaska, a picture taken in the late 19th century. We can go to that exact same spot right now and see what it looks like. And it's a very, very different place. Right? There's been a massive retreat. Tundra has been replaced with trees. Ice sheets have retreated many kilometers. And we can go anywhere and see this, whether it's in the Rockies or in the Himalayas or the Andes or in the Alps or glaciers in Papua New Guinea. I don't know if people were aware that there were glaciers in Papua New Guinea, but literally you have like 2 weeks left to see them. There's massive changes in all of the ice on the planet, and that's a very good measure of what the planet is seeing, because those are integrated measures. They take account of changes over many decades, not just the weather today, which can be quite noisy. We can go and measure things more precisely. These are measurements from the GRACE satellites that are measuring the gravity of the Earth, and they tell us where gravity is changing. And gravity has changed since 2003, most of all in the ice sheet region. So in West Antarctica, around Greenland, where if you add up the total amount of mass that's changed, we're losing 150 gigatons of ice per year from Antarctica, about 280 gigatons of ice per year from Greenland. Those are massive changes that are having a very direct and measurable impact on sea level. And sea level is rising. We know that sea level is rising. We're measuring it at the coastal tide gauge stations. We're measuring it with laser altimeters, and we're measuring it in the impacts of things like coastal flooding. Coastal flooding in the US is increasing exponentially. Why is that? That's because the water is rising, and as you go up that curve, it's an exponential rise from those low extreme numbers. So we know that what is happening is having an effect. We know that on a planetary scale, what is happening is large and of geological significance. But how do we understand all of these things? So this has been a process, right? We have been thinking about this seriously, I think, since the 1950s, certainly since the 1960s. And our efforts to build models to understand the phenomena that we are seeing or that we think that we might see has been ongoing through that time. But there's been a very interesting development over that time period. Back in the 1950s and 60s, the work of climate modeling was done in a very disciplinary basis. So the meteorologists wanted a model, the oceanographers wanted a model, the people that cared about carbon wanted a model, the people that cared about atmospheric chemistry, they had their model, the carbon cycle people had their model. But people realized over time, I mean, they always knew that this was a couple problem, but over time, the resources and the interest and the funding arrived to allow us to start to really think about this in a coupled framework. And so that involved bringing together disparate groups, the atmosphere people and the ocean people and the cryosphere people and the aerosol and the composition people and the biogeochemical people and the ice sheet people and the vegetation people and the dust people, all of those people, bringing them together to work on a common framework. And so the current climate models, the current generation of climate models has really been a process of assimilation and integration of all of those disparate groups and topics over the last almost 60 years. And as time has gone on, more and more complexity has been included, more and more detail has been included, and I'm going to argue more and more skill has been shown. But it's very much a synthesis of lots of disparate pieces of information. And I think that's a necessary impetus that we need in the scientific field to kind of counteract the kind of natural tendency to get ever more specialized and reductionist. This issue, this topic, these models are helping us bring all of that together. So if some of you may be aware of the lumpers versus splitters dichotomy in science, well, people that are working on climate models, they're the lumpers. We're lumping everything together. And that's, we need the splitters too, but we're the lumpers. I want to bring out one other thing, which is kind of the generation of climate models. Since the 1990s, the groups that build climate models have got together and have defined among themselves interesting experiments to do with their models and baselines for which to do them, so that we can compare those models both amongst themselves and with each other. And so this project is called CMIP, the Coupling Model Intercomparison Project. Started off in the 1990s, kind of really got going in the early 2000s with CMIP 3, has skipped CMIP 4 for unknown reasons. CMIP 5 was kind of in the early 2010s, and we're just kind of finishing up or in the middle of CMIP 6, the 6th phase of this project kind of right now. So just bear those acronyms in mind for a little bit later. How do you build a model? Right? What's the process by which we do this? Well, the first thing to know is that it's a circular process. It's never ending, and that's good for my career. Not so great for the planet, but what can you do? We first start off with our best estimates for the boundary conditions. What's on the land, what's the shape of the land, what's the height of the land, what are the emissions that we're putting into the atmosphere, where are these things coming from. All of those things, we are continually revising those because they're changing also, but we also have better estimates over time. We develop parameterizations, we develop ways to capture the phenomena of things that we can't resolve explicitly, like the behavior of clouds or the behavior of small-scale wind gusts or eddies in the ocean. We build those parameterizations to capture the phenomenology that you see, and then we build these things into the model along with conservations of mass and energy and water, along with the equations of fluid motion, along with the equations of radiative transfer. And we put it all together, and then we have still some scope to play with things. We've got some unknown parameters which we have kind of constrained, but we don't really know what they are. We can play with those to try and get a calibrated model to the present day as best we can. For that, right now we're using machine learning. We're using lots of different new techniques to do a better job of that than we've been able to do. Then we evaluate those models. We see how well they compare to the observations. We use them to answer specific questions as best we can. But then we find flaws, we find problems, and so the cycle starts again. We update the boundary conditions and the parameterizations and the tuning and the evaluations. And so we have that cycle that's kind of always ongoing, that has been kind of punctuated by these CMIP intercomparisons every so often. So, quick question. Given all of that, do we have any right to expect that imperfect and incomplete models of complex phenomena should provide skillful predictions? It's not obvious, right? It's not obvious that the answer is yes. But I'm going to show you that the answer is, in fact, yes. And I'm going to try and explain why that is. Let's go back to the 1960s. Manabe, who's just won the Nobel Prize for basically this paper that was written the year I was born, weirdly. And what it shows is in this figure is what happens when you increase the amount of carbon dioxide in the atmosphere. And you can't quite see right at the bottom there, but what's happening is that the temperatures at the surface are increasing, while the temperatures above the tropopause are decreasing. So you have tropospheric warming and stratospheric cooling. And it's a very different pattern than you would expect if, for instance, the sun was getting warmer. Then you would see warming at both the surface and in the stratosphere. The amazing thing about this paper is that they don't mention the stratospheric cooling part of this figure at all, and yet it's one of the most important predictions that they made. Here's another test of our models. These are spectra taken 20 years apart, well, 27, almost 30 years apart. And the difference between them, you can just barely see that there is a difference between them, is effectively determined by things like water vapor and temperatures and methane and carbon dioxide. And our ability to model that using radiative transfer code is extremely good. So the two lines there that you see in the lower panel, the observed difference and the model difference, are basically indistinguishable, except at very, very fine resolution. And so our understanding of radiative transfer, which is really where our basic understanding of climate change comes from, is actually very good. Back in the 1970s and 80s, we started coupling that radiative transfer code with dynamics with weather, and Jim Hansen in 1988, Manabe again in 1989, both made predictions for what would happen, not just to the global mean temperatures, but to the spatial patterns of temperature as we increase the amount of carbon dioxide in the atmosphere. As we added in more things in the 1990s and 2000s, we did the chemistry coupling, looking at the impact of the ozone hole, the connections of the ozone hole to climate change, and found that global warming would delay the recovery of the ozone hole because that stratospheric cooling would cause a problem. We have worked out that the feedbacks associated with ozone amplify the effect of solar cycles, particularly in the stratosphere. That turns out to be a very important test of the models. And we've found that the impacts of atmospheric chemistry end up increasing the impact that methane has on climate by about a factor of 2 over what you might have thought, just based on its own radiative properties. And that's via reactions that lead to tropospheric ozone. And so the ozone, methane, solar, global warming connections are all very, very clear. And we've been working on those now for about 20 years. How do I tell if a model is any good, right? So I'm going to introduce a concept called skill. That seems like a reasonable thing to do, but I'm going to define it quite specifically as being a model is skillful if it gives better predictions than a simpler alternative. Right. So if I can tell whether the model is giving me more information than I had before, then it's skillful. If it's not doing any better than what I could have done without it, then what was the point? Okay, so the question is, have these models been skillful? So go back to the original result from Manabe, that as carbon dioxide is going to increase, the stratosphere should cool and the troposphere should warm. Voila, indeed, the stratosphere has cooled and the troposphere has warmed. And there's other things that are going on in these temperatures. You can see effects of volcanoes, you can see effects of El Niños, you can see, if you look carefully, the effects of ozone depletion and the stabilization of the ozone hole since then. But you can add up all of those different things and you can understand all of the patterns that you're seeing there. But this was predicted, and it was predicted before we had any measurements of temperature in the stratosphere. That's pretty impressive. The temperature changes over time. This was a simple model in 1981, underestimated the changes to global temperatures. Hansen's predictions in 1988, or published in 98, made in 1984, turned out to bracket where we've ended up going for reasonable reasons. In the 2000s, those CMIP3 models ended up having a very, very good prediction of exactly where the planet would end up, which is a little surprising, but nonetheless pretty impressive. And then CMIP5, you can see that there's a little bit of a narrowing of that band of uncertainty because we got a little bit more clever, or well, a little bit more sophisticated, maybe not clever, in how we did the forcings, and those model predictions have also been skillful. But not just in the global mean. If you look at the regional patterns, what you see is that same skill coming out. This is the observations in the model going through the 20th century. The blue and the white there, the blue and the yellow, there's kind of weather patterns. You can see some patterns, you can see some ENSO type things. It's been smooth, so it doesn't get too much in the way. But then kind of 1980s, the 1990s, now we're seeing something new, 2000s, 2010s, we're seeing a new pattern emerge. Something else has occurred. And that's the pattern associated with global warming. And we can see that the models and the observations match not just in the global mean, but also in the patterns that you see. The fact that the land is warming more than the ocean, the fact that the north is warming more than the south, the fact that the Arctic is warming most of all. Those are very, very robust, predicted and skillful patterns. But we also need to know that we're getting it right for the right reasons. One of the things that was predicted back in the 80s and 90s was that if we were doing this for the right reasons, right? If we understood things, if we understood that the greenhouse gases were causing a radiative imbalance, there was more energy coming into the system than there was leaving. Where does that energy go? That energy has to go into the ocean, because that's the flywheel of the climate. That's where the vast majority of the heat capacity is in the ocean. But in the 1980s and 90s, we did not have good estimates for what the ocean heat content was doing. It turns out that would take another 10 or 20 years to get right, pulling the data together, dealing with the non-climatic biases, and then having enough computer power to kind of really bring together those millions of measurements. And it turns out that by 2005, we did have enough evidence to see, how is the ocean heat content changing? Is it changing at the same rate that the models have been predicting? And the answer is yes. And so we published this in 2005. We went back to that in 2012. And what you can see, and what's been robustly demonstrated since then, is that the heat content in the ocean is rising at the right level for carbon dioxide effectively to be the dominant factor in causing those long-term trends. We've also used these models for natural experiments, for understanding what was going to happen, for instance, after the eruption of Mount Pinatubo, right? So that happened in June 1991. And within 3 months of that, Jim and his group had run these experiments, published these experiments by the end of October, accepted in the end of October, it appeared in January 1992. So this is before anything had really happened. And they predicted that in 1992 and 1993, the planet would cool by about a maximum of about 0.5 degree. And that was done before any of that happened. So what happened? Well, the planet did in fact cool, not quite by as much as was predicted, because there was a big El Nino event which was not predicted and could not be predicted by this setup in 92, 93. But the overall cooling was very good. And then subsequently, when we've gone back and done hindcast with better estimates of the aerosol depth, then we end up with model estimates of the impacts of Mount Pinatubo that match the observations effectively to a T. I discussed skill as a concept. Well, we can operationalize that. We can calculate how skillful particular models are against, in this case, temperature and rainfall patterns. And here you can see those 3 generations of models: CMIP3 from about 20 years ago, CMIP5 a decade ago, CMIP6 current. And what you can see is that the skill here is small bars are more skillful. So these are the errors. So the big long bars, those are very those are models with a lot of error. Each of the bars is a different model that was submitted, and you can see that overall CMIP3 and CMIP5 is more skillful, CMIP6 is more skillful, but there's still a spread, right? There's still a spread of model skill. The worst models in each generation are better than the worst models in the previous generation, and the best models are also better than the best models in each previous generation. And on average, the models are getting better. But there's still a wide range of skill. Now, the tricky thing, though, is that depending on what the metric is that you're using, the models move around, right? So there isn't one model that's the best at everything, and the model that can be the worst at one thing can be the best in the next thing. And so you see very similar patterns regardless of how you measure the skill, but the specifics of each individual model moves around quite a lot. You can see these improvements in things like teleconnections, right? So these are actually quite complex emergent properties of the model. Effectively, when you have an El Nino event in the Pacific, what are the far field impacts of that? What does that look like? And these histograms, density plots, give you how well the models do across the ensemble as a function of time. So the light blue is the CMIP3 runs, and so, for instance, the teleconnections associated with ENSO, the correlations were all over the place. In CMIP5, they got a little bit better. In CMIP6, they're better still. And the same thing for the PDO, the Pacific Decadal Oscillation. The large-scale teleconnections are getting much, much better as the models improve over time. But there are still problems, right? And one of the biggest fields where there's almost always problems is in the marine stratus region. So these are the low clouds on the western sides of the continents. So you can see, I don't know if you can see my cursor. Can you see my cursor? Here off the coast of California, off the coast of Peru, Namibia, those are areas where there's a lot of low cloud that the models kind of have a hard time getting exactly right. And that's because there's a lot of very small scale things that are going on. You need a lot of high resolution in the vertical, and we collectively have not quite got there yet. So the models are still doing some things not quite right. Little break for the philosophers here. All models are wrong, right? So let's just put that out there. We're not discussing whether models are right or wrong. They're all wrong. The only interesting question is whether they are useful, right? And it's much easier to see that models are wrong when you're looking at a climate model than when you're looking at quantum mechanics. But quantum mechanics is wrong too, as is general relativity, as is any other physical model that you would care to mention. So here's part of our problems. This is a slide that I stole from Reto Nuti, and each of these is a jumbo jet. They all seem serviceable. There's probably some variation in fuel economy, top speed, capacity, all those kinds of things. And you can think of those a little bit like all the different climate models. But the average jet is not really something you would want to fly, right? And yet, if you recall, when I showed you the predictions from CMIP3, I averaged them all together, and the big line that went through the middle of the observations was, in fact, the average of all of the jumbo jets in modeling space. And it does actually quite a good job. And that's, up until now, has been kind of a surprise and slightly problematic. What we call this in the jargon is model democracy. One model, one vote. And you don't really care about where that model is from or what its skill level is. You just throw it all into the mix, and then you average it together. Now, clearly, that is the worst weighting scheme that you could come up with, right? Except it's pretty good. And up until very recently, that was the standard that one had to beat. Could your model do better than the average of all of the models? And it was very, very hard to do so. And so people kind of stopped trying for a little bit. But now something has happened. This has happened. CMIP6 has happened. This is a histogram of climate sensitivity. So climate sensitivity, for those who aren't in the know, is what happens when you double the amount of carbon dioxide in the model and you see what temperature it gets to eventually. Right. And so we think that number is around 3 degrees Celsius. So that's kind of just to the left of the center there. But these are the estimates from the different models that were in CMIP6, right? So this new comparison of all those different climate models. And you can see some models here that have this climate sensitivity term that is almost at 6 degrees, kind of like twice as high as we really think it is. And there are some models that have climate sensitivities almost half that, right? It turns out that those are the Russian models, which I'd like to say we're segregating for political reasons, but no, we're segregating for performance reasons. And the IPCC makes an assessment of what the likely values of the equilibrium climate sensitivity are, and that's that bar that you can see in the middle here. This is the very likely and then the likely range here, and it kind of, you can see that it's centered just above 3, but basically anything between around 2.5 and 4 I think would be an acceptable value based on additional constraints, external constraints to the models. And so we have this odd situation that now the models are giving a larger spread to this important number than we can constrain. And this is the first time that that's happened. If I plotted the CMIP5 models here, they would all fall inside these bars. And so this is a new phenomenon. And basically it's broken climate, it's broken model democracy. And I'll give you an example of that before. Now, why does this matter? It matters because of this. If we had observations of the future, we would obviously trust them more than the models. But unfortunately, observations of the future are not available at this time. And that's always going to be true. So if we want to have predictions of the future, we need to rely on models. But can we rely on the models? That is the question. And this is what's happening with the CMIP6 models. This is the temperature changes from the pre-industrial in a kind of mid-range scenario for the future. So we're starting in 2015 here, going out to 2100, and each of the little gray lines is an individual model, and the mean of all the models is this dashed line. That's the model democracy. And then there's this, the solid line is the IPCC assessed warming. So in the AR6 report that just came out, they use the models, yes, but then they use external constraints to make a prediction about how the temperatures would change that turns out to be quite different from the mean of all the models for the first time. And is very different from what you see in what we're calling these high ECS models. So models with a high climate sensitivity above 4.5, say. And there is such a large gap now that we can't, in all good faith, keep averaging all the models and hoping that they're going to give us the best estimate. We now need to take those models and constrain them. And when we're looking at the future, we have to be looking at constrained estimates of the future, not just throwing all the models into the hopper and seeing what happens. We have a comment that's going to be coming out in Nature at the beginning of May that I think will go into this in some more detail, and so you can look out for that. But what we're going to do is actually much more driven by the scenario, by what we're going to do as a society, than it is the uncertainty and the climate sensitivity. These are three different scenarios. The one down at the bottom, the burn it all scenario, that is effectively we find all the hydrocarbons that we can and we burn them all. Aggressive mitigation would be something that would be consistent with the goals of the Paris Agreement. Serious mitigation might be something that kind of follows what people have pledged to do now, which isn't quite sufficient to get to the goals of the Paris Agreement. But what you're seeing here is that there's still going to be, regardless of what we do, ongoing changes, particularly in the Arctic. But the changes that we're going to see, or that we would see in the worst case scenarios, these burn it all scenarios, are so much worse than the situation with mitigation that it's really kind of terrifying. But even with serious mitigation, you can see the temperature changes in the Arctic. We're looking at another 3-4 degrees Celsius in the global mean, in the Arctic mean, which is incompatible with summer sea ice. So you know, we can still expect to see rapid and very large changes in the Arctic and in Greenland and in Antarctica as a function of those increases in greenhouse gases. Hopefully we can avoid the situation that we see there at the end. And that kind of leads us to a kind of a tricky question, which I'm sure that many of you are dealing with. We have got skillful models. We have got a good understanding of what's happening. And Sherwood Rowland, who won the Nobel Prize for the understanding of the chemistry of ozone depletion, said much later after this, he says, what's the use of having developed a science well enough to make predictions if in the end all we're willing to do is stand around and wait for them to come true? And we're all in this position now where we are making predictions that as scientists are a triumph. We have wrestled information from the universe. We have measured things. We have understood processes. We have put all these things together. We have synthesized this information, and we are making skillful and important predictions. Yet we're making predictions that we don't want to come true. And so when they do come true, it's confusing because, you know, wearing our scientist hat, we're happy that our predictions are true, right? That's a great intellectual triumph. But wearing our citizen's hat, we would rather have been wrong. We don't want these things to be happening. And so people who are building these models that are basically ways to make better predictions, we're making better predictions based that are ever more depressing. And so we have to think about what it is that we're doing and why. Do we need to be doing more of this? I would answer yes, because there's a lot of uncertainty in these models, particularly when it gets to those regional impacts, when it gets to the changes in things that really do make a difference, the extreme events, the extreme heat waves, the extreme rainfall, all of which are predicted in the aggregate by these models, but perhaps not at the quantitative way that we actually need to help people prepare, not just to mitigate, but also to adapt to the changes that are coming. We need to use all of our resources. We need to use our new tools with machine learning. We need to use our new and faster computers. We need to use our new and better data. But we have some fundamental issues that we need to address. Why, for instance, did the CMIP models expand in uncertainty from as they grew more sophisticated? It's because we are putting in processes that have gotten ahead of the observations. And those processes involve cloud microphysics. They involve aerosol indirect effects that we cannot currently constrain from observations. And so people are putting in ideas, but those ideas are unconstrained, and so the uncertainty is increasing. That's a problem. We need to get better at constraining those things, and we will. Where NASA is flying satellites that will do a much better job of measuring those aerosols, that will do a much better job at measuring those intersections between aerosols and clouds, and the small scale processes that inform the parameterizations that we use in those models. But it's going to take a while to do that. And so in the meantime, we're stuck with this situation where we're making predictions, we understand what's happening, and we just don't want them to carry on. And so we all have to find a balance between carrying on our science as usual and then thinking about being our citizens as usual in trying to avoid outcomes that we don't want to see. And your whole institute is based on this notion that we can become more sustainable, and this is really the challenge of the moment, but not just of this moment, but of many decades to come. So with that, I shall thank you very much for having me.
Thank you so much, Gavin. Thank you for a very nice talk. So we have questions. If you have more questions, please put them in the Q&A. And let's see. How should we do this? I can call on the people that have asked questions and allow them to ask their question live.
I can just read it as well and just respond. That might be the easiest way.
Okay, let's do that.
Okay, so I'll start off with there's one question in the chat from Noe Nava. Out of curiosity, can you explain why the average of the models works really well? The answer is no, I cannot. And the reason why I cannot is that you can't apply the law of large numbers here. These are not random climate models that I've taken out of a hat that, I can then kind of, if I just average them out like a poll, then, the error is going to go down. That's not what happens. When you average the models together, the error goes down initially, but then it saturates. It doesn't look like these are random models. They look like they're models of something that isn't quite real, and then there's some noise. And it's very, it's a little bit of a mystery why the model average outperforms even the best model. One would not have anticipated that. And so if you can work out why that is, then that's a Nature paper right there for you. Okay, so now moving to the Q&A. From Sunday Delerba. Forgive me if I don't pronounce these things correctly. What are my views on geoengineering? Mount Pinatubo was a natural experiment and cooled the Earth. So could geoengineering be a solution? Okay, well, let's pass that a little bit. A solution for what? You can ask a physical question. Should we put in sulfates into the stratosphere? Would that cool the climate? The answer is yes. Would it also have bad effects on stratospheric ozone? Yes. Would it cause issues with acid rain in the high latitudes? Yes, it would. But yes, it would cool the climate. But for it to be a solution, you have to think about what that would look like. And my objections to geoengineering are very much more in the governance realm than in the physics of it. right? So I think we know the physics well enough to be able to say, yes, that it would work. But then think about how it would actually work in practice. So, you could say, okay, well, all the countries in the world are going to get together and set a policy that would be equitable and appropriate for everybody. Well, that doesn't sound very likely, right? So what's more likely is a large country with very weak legal or environmental controls might just decide to do it. China. And they could do that. We would detect it very quickly, instantly, in fact. And then what would happen for geoengineering to be a solution to climate change? It has to persist until carbon dioxide is at net zero, right? So if people use it as a crutch to avoid reducing carbon emissions, then effectively you're saying you have to do geoengineering forever. Now, if you forever, I mean decades and decades and hundreds of years, and that means beyond any kind of political timescales, beyond, it has to be, you'd have to keep it going through different regimes, through different wars, through different economic crises, through different technological things, through different, election cycles, and you'd still have to keep it going. Because if you stopped, the impact of stopping geoengineering is far, far worse than the impact of the climate changes that we've seen now, because it would change the temperature of the planet by a degree, like literally in a year, and that's crazy to contemplate. So what would happen though if something went wrong? What would happen the first time that there's a failure of the Indian monsoon in a geoengineering environment? Are the Indians going to wait for a peer-reviewed detection and attribution study that either does or does not blame the geoengineering for their monsoon failure? I don't think so. And so now we have a situation where two different nuclear-powered countries are kind of arguing about existential threats to their existence based on a geoengineering scenario. That's also terrifying. And so when people say, is geoengineering a solution, I think they have to phrase it as, is geoengineering a sustainable solution? And I don't see any way with the current geopolitical framework that we could sustain geoengineering long enough for it to be a solution. So I find it mostly a distraction to talk about the physics of geoengineering, because there is no sustainable solution that allows for geoengineering to play a role. Second question, what are the improvements in future climate models that current models are missing? So there are a lot of small-scale processes associated with ice nucleation, aerosol cloud effects. I think there's going to be a lot more work done there. But then there are other things which I think people aren't working on quite so much that are just as important. So the interaction with the ice sheets, particularly in the Southern Ocean. So I mentioned earlier that the ice sheets are losing mass, right? And that fresh water is going into the ocean. It's changing the stratification in the Southern Ocean. It's actually leading to slight cooling around Antarctica that is in kind of contradiction to what the average of the models say should be happening, because the models don't have this impact of the fresh water on the Southern Ocean. So we need to be including those things. We need to be doing a better job on sea level. We need to be doing a better job with the with vegetation responses, with human responses. A lot of the times when we do these scenarios, we're just assuming some guess about what human activity will do, including things like what crops they're going to plant or how they're going to irrigate. But obviously those things are in fact responding to the climate change. So you can't really have the climate change and those responses be determined independently. So they need to be coupled, but it's very, very hard to couple human decision-making with physical variables in any kind of skillful way. So people are working on that, and I think that that's quite an exciting frontier that might allow for more realistic scenarios to be used. Next question, Rachel Freeman. Is there an ongoing collaboration between climate models and global integrated assessment models? Can we use them to develop, can outputs from IAMs be used to develop constraints for climate models? That's a tricky question. So the scenarios that the climate models use are from integrated assessment models, but the integrated assessment models are not really coherent with the climate changes that the climate models then produce. Can the IAMs produce outputs that can constrain the climate models? That's trickier. No, I don't think so. Maybe you'd like to expand on that. I'm not quite sure what that would look like. You have another question. Can you talk about how well the models represent natural buffering effects and tipping points, and what importance that has for mitigation options? So tipping points, I'm a little uncomfortable about that discussion. There are clearly lots of thresholds in the climate system, and the models represent those things. There are thresholds when you don't get any ice. There are thresholds when the circulation of the North Atlantic collapses. There are thresholds for tropical cyclone genesis, those kinds of things. There are thresholds for viability of agriculture and vegetation in drought situations. I mean, all of those things are effectively already in the model, and there are lots of buffering effects. I mean, the heat capacity of the ocean is a massive buffer to the climate changes that we're putting into the atmosphere. But a lot of the discussion about tipping points is odd. Because they kind of assume that there's like one big tipping point for the whole planet. Often people assume that it's associated with 1.5 degrees or 2 degrees, but none of those things are tipping points. And I'm not really aware that there's any tipping points at the global scale that would really change the damages curve in any sharp way. So as temperature changes increase, we expect damages to increase, and we expect damages to increase kind of exponentially as temperatures increase. And so there's a non-linearity there, but I don't think there's a tipping point. I don't think there's ever a point at which it will not make sense to be doing the right thing, or that it will be out of our hands. One of the interesting things that's come out of the most recent sets of models is that when we do what's called a zero emission commitment, so that means, what happens to the climate when we cease all emissions immediately? What happens is that the temperatures no longer increase. And that means that temperature changes in the future are really a function of emissions in the future. And so that means that we are in control of what's going to happen. And that means that there's always going to be like things that are better for the climate and things that are worse for the climate. There's never going to be a point where it's not worth doing something. And if you, before you get to the tipping point, people, I think, maybe get a little complacent. Well, we don't need to do anything because, we're not near that tipping point. I think that is, that kind of leads to complacency. So I don't like the tipping point framing of what's happening.
Two more questions, so we don't keep you here too long.
Oh, okay. Well, oh, geez, there's a lot of questions. Okay, let me let's just go quickly. Okay, where else? Sonia, will the names of the models that are in the wolf pack be released in notes? Yes, they will. Yes, they will. But you know which ones they are. The CESM2, the Hadley Center models, E3SM, the DOE model, CAN ESM5. Yeah, I am totally happy to name names. Am I confident that scary feedbacks like runaway methane emissions are unlikely? I actually, yes. So the runaway methane emissions story is mostly nonsense. If you look at times in the past when the Arctic was warmer than it is even now, there's no sign of any massive methane feedback that we can detect in the ice cores. And a lot of the work that led to this idea that there would be a massive methane feedback, not just a little methane feedback, is based on some rather, what's a good way of putting it? Heroic assumptions, let's say that. Is there a subset of models that perform better than the average of all models? No, not as far as we can tell. How do we acknowledge climate model uncertainty while building political and public trust in climate science? I think we just need to be honest about what the uncertainties are. I mean, like I said at the beginning, more models are wrong, and so we don't need to pretend that they're perfect in order for them to be useful. I think we just need to frame things as these models are useful, and they're telling us how things are going to happen, and we can rely on many aspects of what they're doing. And here's the tests for how you can rely on it. But you can't rely on everything they give you. That's unfortunate. But in the same way that you can't rely on a 20-day weather forecast, people seem to live with that kind of uncertainty too. As a climate science, what are the best types of activism to make progress? So I think that we all wear many hats, and we all have many different paths to have our voice be heard. You know, I sometimes appear on TV. You can write letters to your congressperson. You can go to town halls. You can talk to your friends and your families. You are consumers. You are parents. You are homeowners. I mean, obviously not all of you all at once, but in general, we are able to make decisions that have a bigger impact than just our consumer choices or just our voting patterns. And I think that we should use all of those hats that we can wear as much as we can. Why are low-level stratus clouds so tricky? It's because they are kind of sandwiched between a down large-scale subsidence of air and turbulence at the bottom, and that's a very small window. You need a lot of vertical resolution to be able to resolve that. Up until very recently, most models have not had that level of detail, and so it's only recently that that models have started to get a lot better with that. Does climate already define the planted area, presumably for agriculture? Yes, and the climate change is going to change the planted area. Yep. Paul, is it possible to set up initial conditions to 1900 and run the CMIP6 models forward? Yes, that's exactly what we've done. We've started in 1850 actually, and then we ran them forward. And we do know the answer until 2020. And yes, we can eliminate those that don't get it right. But the problem with that is that there's a number of ways that they might not get it right. One of them might be the climate sensitivity. right? Which would be a valid way of screening things going forward. But another one might be the drivers that we put in, and particularly what we did for the aerosols, which, as I mentioned earlier, are still unknown, and the intersections of aerosols and clouds are still unknown. So it may well be that your model is fine in terms of climate sensitivity, but it doesn't quite look like the 20th century because it got the aerosols wrong. And so would it be right to penalize that model because of an input, even though all the processes are right? And it's very difficult to tell the difference there. So effectively, people are trying to do that. And there's a couple of papers that have tried to do that. Tokarska et al. In 2020, for instance, and in the IPCC report, they effectively did this. But there are reasons why it might not work. Okay, whoa, that was it.
That was impressive. Well,
there's one person with a raised hand. Oh no, it's gone. Never mind.
Well, let's thank Gavin so much. It was a pleasure having you here, and we hope to see you again.
Yeah, if there's anything that came up that you want to ping me on, I'm actually pretty easy to find. You can email me at gavin.a.schmidt@nasa.gov, or if you're a Twitter person, I'm at Climate of Gavin. So feel free to reach out if there's anything else that I can help you with. Or do you want to help me with? That would be great too.